For the design of a machine element, we should understand the types of stresses the member is going to experience and the maximum stress induced in the member due to the application of forces in the axial direction, whether it is tensile or compressive, or in the lateral direction, the shear, or the lateral direction which results in bending stress, or the member is subjected to a twisting moment, that is torsion. So depending upon the types of forces experienced by the member is going to experience stress. So in today's session, let us discuss the simple stresses, the tension and compression. In simple terms, stress is the resistance offered by the body to the externally applied forces. It may be a single force, it may be a system of forces. Stress mathematically is the force applied by the cross-sectional area. The area is the resisting area and force is the applied force in the normal direction to the cross-sectional area. The units are, in SI unit we take Pascal, that is Newton per meter square. The more commonly used units are megapascal or Newton per mm square. Strain. When the body is subjected to a force or a system of forces, the forces does the deformation of they try to deform the body. So the change in dimension to the original dimension in the direction of the applied force is known as the strain. Delta L by L, where delta L is the change in length to the original length if it is applied in the axial direction. Tensile stress. When the body is subjected to force in the axial direction, which tends to elongate the member. If you take a section at X, at the section X on the left hand side, there will be the resisting force on the right hand side, and the right side portion at the section there will be left side force. That force upon the cross sectional area at this section is known as the stress. At the junction, the stress on the left hand side is equal to the right hand side for the equilibrium. Compressive stress. When the body is subjected to an axial force which is equal and opposite in direction, and that results in the reduced dimension in the direction of force, whereas tension is the increased dimension in the direction of force. The two forces are acting away from each other, results in tension. The two forces that are acting towards each other in the same line of action, that results in the compression. The compression results in reduced dimension or contraction, whereas tension results in the increased dimension or extension of the member. Young's modulus or modulus of elasticity. The Hooke's law states that the stress is proportional to strain within the elastic limit, and this is replaced with the modulus of elasticity. Then stress is equal to the modulus of elasticity capital E into the strain, or modulus of elasticity capital E is equal to stress by strain. So stress is mathematically load by area and strain is mathematically delta L by L. By rearranging these things, the modulus of elasticity capital E is equal to P into L by A into delta L. The modulus of elasticity in practical terms, it is represented in gigapascal or megapascal. Shear stress and shear strain. So when the member is subjected to, here you can see in this diagram, a rivet is the member which is under consideration, which is used to connect the two plates. There are two plates, one plate is in the pink color and another plate is in the blue color. These two plates are connected by a member called rivet. When the two plates are subjected to forces like this, the pink one is pulled to the left and the blue one is pulled to the right, and that results in the force on the rivet which is in the tangential direction to its cross section. That force is acting along the cross section. So that results in the shear of the member. That means the rivet is going to cut along the force. So here at the junction of the two plates, the shearing or cutting of the rivet is going to take place. The shear stress is equal to the force applied if the two forces are equal and the force P is divided by the resisting area. That means the resisting is applied by the cross section of the rivet. So that is the resisting area pi by 4 d square, and shear stress is equal to the shear force or the tangential force upon the resisting area. When you have such kind of joint where two plates are joined together by help of two cover plates. This is the cover plate on the top and this is another cover plate at the bottom. This is also known as a double strap. A riveted joint with the double straps or two cover plates, and this is known as a butt joint with the two cover plates. When you have a cover plate, it is known as a butt joint. When you have like this, it is a lap joint. In a lap joint, rivet is subjected to single shear. In a butt joint with a single cover plate, the rivet is subjected to single shear. But in a butt joint with two cover plates, the member, the rivet under consideration, is subjected to double shear. So here, when the two plates are pulled away from each other, that results in shearing of the rivet at two places. At the junction of the top cover plate with the main plate and at the junction of bottom cover plate with main plate, at two places the shearing or the cutting of the rivet along the tangential force or in the direction of tangential force is going to happen. This is known as a double shear. Shear modulus or modulus of rigidity. The shear stress is proportional to the shear strain, and the proportionality constant, the modulus of rigidity, C, or it is also known as a G, and this shear stress tau is equal to proportionality constant C into phi, the shear strain. When they are rearranged, shear stress tau by shear strain phi is equal to modulus of rigidity C. This is also expressed in gigapascal units. The other types of stresses are bearing stress or bearing pressure. So when we take the same example of the lap joint, the two plates, the above one is pink and below one is blue, and they are connected with a rivet here. The applied forces, okay, let us imagine they are not able to shear the rivet, but what is going to happen at the rivet is placed within the plates by drilling a through hole. So in the through hole, the rivet shank is placed. When the plates are pulled apart, the hole in the plate is pressing against the shank of the rivet. Then the shank of the rivet is subjected to a condition called crushing. So it has to be able to bear that stress, therefore it is known as bearing stress, and the plates are trying to crush the shank of the rivet, therefore it is known as the crushing. It is either known as crushing stress or it is also known as bearing stress. In order to come out of the winner of this crushing, it has to bear. Now the bearing or crushing stress is equal to the force applied by the projected area D into the thickness of the plate and N, number of such rivets in a pitch length. So the bearing is not only in riveted joints, we can see it in some other cases like a journal bearing. So here you can see a shaft or journal is rotating in a bearing. So the load, either the self weight of the shaft or the journal or the mountings on the shaft, they are going to create force on the bearing through the shaft. So here, due to the external force that is applied through the journal or the shaft, the bearing is subjected to a pressure called the bearing pressure, and this bearing pressure is equal to the force P that is applied through the journal, and it is applied through a contact area that is known as the projected area. The length of the bearing or the journal inside the bearing, the length of the journal inside the bearing L, and the diameter of the bearing, this is not the projected area. The bearing pressure is equal to the force applied upon the projected area. So we have other types of stresses like thermal stresses. Whenever a body is subjected to heating or cooling, and that also results in stress. When a body is subjected to heating but it is prevented from the expansion, and that results in stress. When the body is subjected to cooling and it prevented from the contraction, so that results in stress. So when you are preventing the expansion, that results in compressive stress. When you are preventing contraction, that results in tensile stress. The change in dimensions of the body when it is subjected to axial loads is very well calculated by the ratio called Poisson's ratio. The Poisson's ratio, which is designated by either 1 by m or mu in some of the textbooks as nu also, and that is equal to lateral strain by linear strain. We know that the strain is a change in dimension to the original dimension. Here linear means along the length, and lateral means the perpendicular direction to the length. So here the force is applied along the length, then the lateral means along the cross section. The change in dimensions of the cross section to the original dimension of the cross section is known as lateral strain. The change in length to the original length is known as linear strain. So you can find out the change in dimensions either in the linear direction or in the lateral direction with the help of the thing called Poisson's ratio, and this Poisson's ratio is given here in the table, and it is starting from the 0.25 minimum for steel to a maximum value of 0.33, and the rubber is having the Poisson's ratio between 0.45 to 0.50, and several engineering materials are having the Poisson's ratio like this: cast iron 0.23 to 27, copper 0.31 to 0.34, brass 0.32 to 0.42, aluminum 0.32 to 0.36, and concrete is very low and 0.08 to 0.18. So with this we are closing this session, and let us meet in another session. Thank you.